Now I'm going to add another generic class called the GravityMover, and what it's going to do is deal with some physics involved with gravity. It's a generic class, so I'm not going to assign it an object, but it might be something you find useful to use in your games. So I need to keep track of a few things here, and I'm going to list them in my my fields. So I'm going to need an int to represent gravity, and also I need a horizontal velocity and a vertical velocity. Now, I can't use the doubles there because these are going to be for moving in pixels along the screen, but I will have a double here, and I'm going to call this the rebound. And this is how sort of elasticy the object or the actor is. So that way, it could bounce and ricochet with 100% of the force it came in with, or I could make it ricochet with just 50, or I could make it not ricochet at all, in which case it just would stop moving in that one direction. So you'll see how the rebound works when you get to play with the behavior yourself. But another thing I'm going to keep track of here is I want to know what kind of collisions happened so that I can process them. And to do that, I'm going to show you a new thing called an enumerated type. So it's going to be public because I want anyone to have access to the collision type, because it's going to be similar to the way we defined constants before, but this basically narrows the scope. So it's going to be public static enum, and static because it doesn't make sense for me to create a new copy of this type every time a gravity mover is created. All gravity movers are going to share this, and it's going to be called collision type. So what I'm going to do here is the type of collisions that I might want to have could look like this, and that means I don't need that semicolon there. I'm going to have this enumerated data type which only has 5 possible values. And again, that's something similar to what we could have done before when we did things like, we could even make it public, static, and I could call this an integer left equals 0. But the advantage here is that if I use an enumerated data type, it's what we call type safe. Collision types can only take on one of these 5 values, whereas an integer, there's nothing wrong for me to say like collision equals 72, and there's no 72 collision. So it basically means that any other programmer who didn't understand the protocol could wreck it like they would here. They would have to abide just by these integers, and if they didn't, Java wouldn't catch them on it. So if you use an enumerated type, it just means Java is going to catch it if you have a programming error, because you're literally limited to using these when you refer to a collision type. So I'm also going to keep track of what the last collision that happened to this object was. And that one I'll make private because I don't want just anyone to be able to mess with it. But so private collision type last collision, and that'll just represent whatever the last thing that the object bumped into was. So we'll initialize some of the stuff in the constructor. And I'm going to start with the gravity equal to 1. Horizontal velocity will be equal to 0, vertical velocity is equal to 0 as well, and the rebound is going to be equal to 0, meaning these are objects that don't bounce. And of course I should initialize the last collision, and this is how you access the objects in there. So collision type dot none represents this field right here. So that way, again, I'm forced to say the collision type is none, and Java will check that this is actually the right type I'm using. So you're less likely to get errors if you do it like this than with constants. Now, I'm also going to call the superclass so that I end up with a bounded actor, and I can start calling on all those things as well. So now that I've got my constructor working, I'm going to put some basic get and set methods for the gravity, velocity, rebound, that kind of stuff. But at this point I don't think you really need to see me do that, so I'm just going to pause for a second and then I'll get those methods in here. So all I've just done there was add the set and get methods for all those variables that we've created where it's appropriate. And now I can use those in my subclasses to be able to set those properties of the object or the actor that's affected by gravity. Now, ACT here is a bit of a protocol. So what I'm going to show you is the protocol that I'm going to use, and it's important that you understand the protocol because your subclasses have to obey it as well in order for it to act properly. You could redefine the whole act, but I think you'll find the protocol, I've put some thought into it. It might not be perfect, and I'm not saying there isn't a better way to do it, but this is one I believe is going to work for most of our problems. So this is what the protocol is going to look like, and I will just write it out here, and then you can, I'll explain it to you in just a second here. But the process actions, basically the first thing you're going to do when you act is you're going to allow the actor to try and do whatever it wants. Now this isn't actually going to move it on the screen. All it's going to do is set everything in motion so that it's ready to take those actions. So how do you set it in motion? That's the vertical and horizontal velocity. It could also be the rebound that you're changing. But basically you're just trying to change things that would affect the movement of the actor. Then what happens is you process the obstacles next. Taking these things into account, processing the obstacles will then say, okay, you can either move exactly as you want and return that, or it takes those obstacles into account and will adjust it. So for example, if the mouse was my actor and it was going off the side of the screen here, then maybe I want it to bounce instead. And that would mean the next location wouldn't be through the screen, it would actually be over here. So process obstacles would return that next location where I'm supposed to go. And then now that I know I have a valid location, I'll move to it. And then applying the physics basically handles the next round to say, okay, if we've moved at a certain distance or height, apply gravity to it, or the rebound or whatever else has happened to our actor, trying to obey these laws of physics. So now that you have a bit of an idea what this protocol is, you can certainly overwrite these methods and change them so that, if you want to make different physics happen or different moves, you're welcome to do that. So we'll start with them each one at a time here. And the first one is a little bit strange, and maybe it'll make some sense to you as you practice a little bit. But the first thing I'm going to do here is with process actions. I'm actually not even going to define it. What I'm going to do here is I'm going to tell Java, I'm going to say this is a public abstract void process actions. That tells Java that this is an abstract method, meaning it's not one I've created, but it will be there when you need it. And the way Java enforces this is any subclass now that is not abstract itself will have to implement this method. So basically, it's when you have a class that's generic and you don't understand and you don't know exactly what the behavior of that method would be because it's not a specific enough class, you can make it abstract. That way, as you make a subclass that gets more and more specific, you'll eventually run into a subclass where it does make sense to process the actions. So I don't know how a GravityMover moves because I'm just managing all the physics here. I'm not really telling you, oh, the left key moves left or right, up, down. I'm just saying the subclasses will have to tell you what process actions does. So Java won't be happy unless I declare this as an abstract class now. But basically this is a way that you declare methods which will later be written by subclasses. Now that I've done that, Java will let me compile this, and because it knows that process actions isn't defined, but when it actually needs to execute it, it'll be there in the subclass. Okay, so the next thing that's going to happen is I need to do this process obstacles method. That one's a little trickier. I think I'm going to save it for last. So we're going to talk about these two, which are simpler. So move is basically just going to be to move to the next location. Public void move location next, and once I've given that command, all I'm going to do is set the location to be the next.getX and next.getY. Now it seems like a little bit overkill. I could just put set location there instead, but this way when I move, a subclass can override that behavior. For example, the subclass might actually want to turn or rotate or do something else in that movement than just move its location. Now, because I've added this method here, someone has that ability. So then the next thing is to apply the physics to this class. And one of the things I'm going to want to know about is whether or not I'm on the ground. So I'll have a public boolean on ground. And all I'm going to do here is see if I've hit the bottom of the screen or maybe gone through it. So I just need the y coordinates here and the heights of things. So the y coordinate will just be to get the y, and the actor's height is going to be to get its image, and get its height. So now I know I'm at the bottom of the screen if the y plus the actor's height divided by 2 is greater than or equal to the world's height. So that means I'm now at the bottom of the screen. And that's what I'm going to be using here as well, because if I hit the ground, then I'm certainly going to have some effects there from the physics that's involved. So let's take a look at what that method might look like. And again, by opening it up with a method here, it's possible that subclasses alter this behavior. So the first thing I'm going to do is check for collisions. So I'm going to say if the last collision is from the collision type top, or the last collision is the collision type bottom, then that means I hit either the top or the bottom. It's going to affect the vertical velocity. So the vertical velocity should be whatever it was times the negative of the rebound. So that's going to, if the rebound was a half, it would take that vertical velocity and half it, because it lost half of its velocity on the rebound. And in our case, this starting with a rebound of 0 means basically when you hit something, it just completely stops you from moving any higher. It hits 0. The negative is to make that rebound, that bounce, happen. So we won't be starting with any initial velocity by setting the rebound to 0. It'll basically stop when it hits the top and then start to fall based on gravity. Now similarly, I'm going to look for, I guess I'll do a little copy and paste here, but similarly I'm going to do the right and left. And this time it's going to affect the horizontal velocity, so I'll add whatever rebound was necessary there. Now, if I didn't have a collision, I might be on the ground, and if that's the case, there was no collision and I'm on the ground, then I don't have any vertical velocity up or down. It's basically I'm just stuck there. Barring all these things, then what I'm going to have is this is my chance to apply gravity. So whatever the vertical velocity was, you can apply it to the gravity. You're going to have to at this point either take some physics or trust me when I say that this is the proper sequence to applying gravity. It starts out in this formula that you might recognize. It would be V naught T minus 1/2 gravity times time squared. But anyways, you can get the velocity at any point is going to be V naught, initial velocity then I guess, minus gravity times time. And that's for velocity at any time. And if I want to know the velocity recursively, which is in this case, the velocity at time t is just going to be the previous velocity plus the gravity. Okay. So in our case, well, it's minus because in our case, well, in the real world, right, when they're falling, you'd go down, but on the graphics screen, it's positive. You'd be falling to go, you'd be adding to make it go down. So we're going to add gravity like this. So those take care of our applying physics and move methods. The next one's a little more challenging, which is to process the obstacles. So I'll explain how I'm going to do this, but just bear with me here that it isn't quite as straightforward as applying the physics and moving. So I'm going to be returning the location that I found which is safe to move to. And to process them, I'm going to need to know about where the screen's edges and the actor's edges are. So I'll make this stuff the actor's edges. So the bottom of the actor is going to be to get the y and add the actor's image dot get height divided by 2. And the top is similar. I'm just going to be subtracting it instead. And I'll do the same thing here for the left and the right. So I'm going to get the x coordinate and subtract get the image dot get width divided by 2. And there's a right side where we also would just add the half the image width. Now if I want to get the screen bottom, it's going to be get world from the actor and get its height. The screen top is 0, and the screen left is 0, and the screen right is just the width of the screen. So now I know where the bounds are, and I'm going to use those to figure out what I'm doing. I also want to figure out how much I can actually move this. So right now I'd like to try and move it by that horizontal velocity, and I'd like to try and move it vertically by the vertical velocity. So here's where now I'm going to check to see if I've actually made a collision and if I need to adjust my trajectory. So if my dy is not 0, and I'm going to borrow from the bounded actor and say I'm not able to move vertically by that amount, this means I've basically hit either the top or bottom of the screen. So here's where I'll distinguish them. If the vertical velocity is greater than 0, then what that means is I'm traveling this way, I hit the bottom of the screen. So the way the collisions are going to work is if there was an obstacle at the bottom of the screen, I've just hit the top of that obstacle. So I know it's the bottom of the screen, but what you want to do is picture it as being like a brick wall at the bottom. That would be that we've actually hit the top of that item. So first thing I'm going to do here is say I've just had a collision, so let's record it, is the collision type top. Now I also want to figure out, I can't go all the way because the vertical velocity doesn't fit. So instead I'm going to back off the amount I'm changing y. So I'm going to just adjust it, and this is the amount that will land it right on the top of the screen. So because I've scaled that one back, I need to scale back the x coordinate as well. So I'm going to round this answer here, but basically what I'm going to do is this will be the percentage that I've scaled back the vertical velocity, because I'm no longer going to move the whole amount, just whatever that was, and I want that same percentage to be reflected by dx. However, these are all integers, so I have to do a quick cast here in order to save the decimal place. So this will now get me the scaled version of that change in x to match along with, because y was cut short in its motion. So it's going to be really similar then if the velocity was negative. I know I hit the top of the screen. And the top of the screen, if you picture there's an obstacle at the top of your computer, you actually hit the bottom of that wall. So the collision type I've just had is the bottom. And I'm going to take the top of the actor minus the screen's top to figure out how far I actually have to move. And I'm going to scale exactly the same way I did before for x. Now, the other thing I could check is maybe I've gone off the left or right side. So if dx is non-zero and same thing, I can't move, that would be the bounded actor's way of telling me I'm out of the screen. And it's going to be very similar in terms of what I'm checking. So I'll, just for speed here, because we're taking up your time here as I do this, I'll do a little copy and paste. If I'm moving with a positive velocity, I'm moving in this direction, and I hit the right side of the screen, but that would be the left side of the obstacle. So this would be a left. And the adjustment I have to make now is to the x. So this time it's going to be the screen right minus the right side of the actor. That'll stop me right at the right edge. And again, I'm going to scale, but this time I'm scaling dy. So it's going to be dx over the horizontal velocity, and I multiply that percentage by dy. So that'll be the same thing here. However, this is going to be slightly different. This time, if you do a little bit of math, you're going to find that it's the left minus the screen left. So here's my dx adjustment now. And if none of those things happened, then I'm going to record that as saying the last collision is collision type none. So now that I've made these adjustments, what I can do in here is return a new location which takes the current x and changes it by whatever the legal amount was that I just found. So now I've got a legal location based on what I was trying to move from the original horizontal and vertical velocities. So that's processed the obstacles here, and it's just put me right to the edge. So if I am going to make the rebound, I'll move right to the edge, but then physics here, this will note, oh, I collided to the left. It'll apply that physics change of the bounce that happened before. Now I'm just going to add a couple helper functions, some things that you might find useful, and that's going to be to jump. So I'm just going to do the math for you here about how you would calculate a jump. So I'm going to have two methods, one that's jump to and a height, and another one which would make the actor jump for, and this would be an int. How many moves do you want to go to get to the top of your jump? So if you said 10 moves, it would be 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. Remember, they're getting shorter because of the gravity with each move, but that would be how many moves to the top you have. So all we have to do is, if you think about what you do when you jump, you just give yourself an initial velocity off of the ground. So that's all we're going to do here is adjust the vertical velocity. Now I've done a bit of the math on this already, but this would be the math that gets you the initial vertical velocity if you ask me to reach a certain height. And the way I've said it is this is the how high you have to get up to, so this is the smallest number of moves to reach at least that height. So it's possible that you go over, and it's probably likely that you go over. Now let's see here. So then we have jump for as the other helper method. The math is a little bit simpler, but this is what, if you give me the moves to the top and I multiply it by gravity, I'll just set that to the negative, and that way the vertical velocity will take off that way as well. So now you have a couple of ways of making the actor jump that you can manipulate. And I'm also going to do one other thing, which is add a delay here, just in case you're not happy with the speed of it. So I'm going to need a private int, the act counter, and I'm going to need another private int for my act delay. And in here, my act counter, I'll start it at 0, and I'll make my delay 1, which basically will mean there's no delay unless you change it. So I'll just go and add those get and set methods. You don't need to see that, so hang on. So here's my act delay and set act delay methods, so that way someone can have access to them. And now all I'm going to do in here is I'm going to say if the act counter mod act delay is 0, then you're welcome to act like you normally would. And every time we go, we'll just keep track that we've done another act. So for example, if you wanted it to delay the gravity to only act every third act, just set delay to 3, and this condition will be true every third time act is called. But anyways, for the default, we're just going to leave it as it was, as act delay equals to 1. So that is the GravityMover class, and we will keep building with it.